Luna is the next company, I think a company which is known to us in the aerospace world. This morning it was mentioned about the Delta 767 tests, and we are seeing something here on fiber optics. The gentlemen are just getting ready. You start to talk as soon as you're ready. You are.
Good afternoon, everyone. My name is Naman Garg. I'm an applications engineer with Luna Innovations. And today I have the pleasure of demonstrating Luna's high-definition fiber optic strain sensing technology for detection of hotspots like defects in composites. Now, fiber has many inherent advantages for structural health monitoring applications. The fiber itself is very small and lightweight, so it's minimally invasive to the structure. And fiber is also immune to EMI, it's chemically inert, has excellent fatigue lifetime, all of which make it very practical for SHM. And if you've used fiber optic sensors for strain sensing, it may have been in the form of FBGs, fiber Bragg gratings, where a single grating or multiple gratings are etched into the fiber to create sensing points. And FBGs are great. They've been used in SHM for several years now. But what if you didn't need the grating in the fiber to measure strain? And what if you could measure strain continuously along the fiber instead of at a few discrete points? Luna has developed a way to do just that, and that's what I'll be showing today. We use standard telecommunication fiber without gratings to measure strain everywhere along the fiber, effectively turning that entire fiber into a sensor. And the measurement principle is actually very similar to gratings. We measure a low amplitude reflection that occurs naturally along the fiber's core, which is referred to as Rayleigh scatter. And that signal is actually much lower in amplitude than from a grated fiber, but it's our ability to detect that small signal that allows us to make measurements at very high spatial resolution. We're reporting sensing points every millimeter or so along that fiber. So this test article here that you see on the table is a composite panel that we manufactured in our materials lab. It's composed of 8 layers of carbon fiber and was manufactured through a wet layup process. And during layup, we embedded an optical fiber into one of the inner layers. And as shown in the screen behind me on the right, the fiber was routed in a snake-like pattern going down and back along the length of that panel. And after layup was complete, the composite was vacuum bagged and cured at temperature. And after curing, we took the remaining fiber and bonded it to the surface in the same pattern. And the end result was a total of about 8 meters of optical fiber. We then drilled 3 holes that you may be able to see here onto the panel and added bolts and stiffening elements to create a noticeable strain gradient through a change in stiffness. So I'll go ahead and pull up the software. So what you see on the screen here is a model that we created of this panel. The top model represents the top layer with the surface bonded fiber, and the bottom model represents the inner layer with the embedded fiber. So I can go ahead and apply cantilever loading to this beam, and we can see the real-time strain update. And we're getting live data from Luna's Odyssey sensing platform. And the white lines that you see on the model represent the fiber path, where we're reporting strain every 625 microns along the fiber, so very high spatial resolution. And we can use that measurement data to interpolate between the fiber paths to create this full strain map that you're seeing on the screen. So I'll hold the beam in downward loading so we can get a closer look at the strain profile. As expected with cantilever loading, the top of the panel is in tension, which is shown in red, and the bottom is in compression, which is shown in blue here. And keeping in mind that the embedded fiber is in a layer below the beam's neutral axis, which is why it's measuring compressive strain. And the other thing to notice here is that we can clearly see the color change due to the strain gradient near that first and third hole, and more prominently near that first hole, because that's where the strain is higher. And that's due to that change in stiffness. And as I deflect the beam upwards, we can now see that change in stiffness in that top middle hole as expected, because that's where the stiffening element is added. So we have hundreds of installations globally using this technology for high-resolution strain measurements, particularly for composites where we may not completely understand how that material or structure will behave under different loading conditions. This technology today is, most useful for also validating FEA models, because having measurement data to create a full strain map is very useful and allows for more accurate validation of those models. And today, the solution is best used for residual strain measurements or periodic ground testing and fatigue testing, and is in a path towards in-flight structural health monitoring. Thank you. And if you would like more information or would like to get a closer look at this demo, we'll have it set up and running at the Luna booth outside.
Thank you very much.
Thank you.
Presentation.